So ICRISAT is headquartered here in Patancheru, Hyderabad in India, but ICRISAT has also a research station in 8 other countries in sub-Saharan Africa. So ICRISAT is already doing quite a bit of work on climate change. For example, on the work with mitigation of climate change with farming communities in sub-Saharan Africa. The work that is done, for example, on water harvesting, also with farming communities, or crop modeling work on forecast modeling with future climates in the scope of the agric work. But today what I want to talk about is a bit on the work that we do at the genetic level on means to address the big challenge that climate change is. But first I should sort of say that there's probably a lot of misconception on the way we look at climate change. Climate change is often seen as those big waves of heat that would burn off crops. That may be true under certain circumstances, but there's also more insidious and hidden effect of even moderate increase in temperature. One of them is, for example, the fact that if temperature increases, the crop development stages go faster. What we call the phenological stages develop quicker, and at the end of the crop we've got less of a duration, then less biomass accumulation and less yield. That's one aspect. But what we, for example, often overlook and that's true under the condition in which ICRISAT is working, under those semi-arid tropical conditions. We work in environments which are dry and hot. And that has a tremendous effect on what we call the plant-water balance. And under climate change, an increase in temperature will increase the effect on the plant-water balance and with a tremendous effect on crop productivity. The suction power from the atmosphere on the crop for water is very high. That's what we can call atmospheric drought. Why it is important is because photosynthesizing, producing biomass for crops under high evaporative demand is extremely water costly. In the work that we have been doing, we have found genetic variation for the capacity of the crop to restrict water losses under those high evaporative demands. And so what we have developed is screenings, ways to identify germplasms that have the capacity to restrict those water losses when the evaporative demand is high. We have developed a large phenotyping platform, what we call high throughput phenotyping, to measure those plant attributes in a high rate and high speed, in a way that it can be quickly used into breeding to develop cultivars that have those plant attributes. So I'll finish by saying that what we have been talking about on the work that we do on the capacity of plant to restrict water losses under high evaporative demand, what's going to be very important under climate change, is not only true for climate change, but it's already true today. We are working in environments that are extremely demanding for water, and so the work that we do is not only for climate change, but it is worth doing today.